Welcome to the Collaborative Core Center for Clinical Research Speaker Series. We appreciate you taking the time to join us today for this presentation. Our presenter today is Dr. Michael R. Kosorok, a W.R. Kenan Jr. Distinguished Professor in the Department of Biostatistics and a professor in the Department of Statistics and Operations Research at the University of North Carolina at Chapel Hill. He is also one of the Associate Directors of UNC Chapel Hill's CCCR Resource Corps. His presentation today is titled Recent Developments and Future Possibilities in Precision Health. Dr. Kosorok, whenever you're ready to start, feel free.
I will. Can everybody hear me?
Yes.
All right. And if I don't notice you're in the chat because I can't see the chat while I have it on full screen mode here. If somebody could maybe let me know that they have a question.
I'll monitor it, so don't worry about it, Dr. Kosorok.
Okay, thank you.
You're welcome.
Well, I'm really excited to talk today. Looking forward to it. I'll be talking about precision health, which is an area of focus for me. And I will give some old and some new examples and talk about some basic concepts as well as some large ideas, I guess, or large at scale, high level ideas. And it's going to try to stay away from theoretical or mathematical content, but I may have to use just a little of that in various places. So this opening slide here, this is a plot of 24 hours in the life of a patient with type 1 diabetes. The black line is the glucose level, blood glucose level. The red dots are insulin boluses. The blue and the green are physical activity and food intake, with the circle is the magnitude, and the event time for that meal or activity starting time is in the center of the circle. So what you can sort of deduce from this plot is this patient tends to be a little bit high in their glucose level for the first bit. They then exercise. We have this big blue circles there, and they're losing their blood glucose concentrations, going down quite quickly, and it gets down to a fairly, definitely lower than optimal, potentially dangerous range. And then they eat a snack to bring themselves out of that, and they take insulin to bring themselves back down, and they kind of alternate, but they eventually get into a pretty good range of glucose, but it takes them the entirety of the day to get to that point. The point I want to illustrate is this is a very challenging health situation where real-time guidance could be very useful at keeping a patient healthy and allowing them to exercise if they have type 1 diabetes. I'll come back to this and talk about precision health questions surrounding this in just a little bit. I do want to talk a little bit about some concepts and what I mean when I talk about precision medicine, precision health. It's fairly specific what I'm referring to. Precision medicine is data-driven decision support for treating patients. And the treatment can include drug choice, administrative actions, the dose, the timing of the drugs, other potentially modifiable risk factors. For example, one could look at this as what are the what behavioral habits should a person develop to help optimize outcome of health. But the kind of algorithms we're looking for were those that are data-driven, that are reproducible, they have inferential properties, meaning that they can be applied to future patients as well as generalized under reasonable conditions. Precision public health, and so one of the key ingredients I'll talk about in just a minute is the idea of estimating an algorithm for how to treat patients. Precision public health is the taking of this idea but applying it to families and clinics, communities, hospitals, social networks, other groups and settings where individualized actions that are guided by the context can really lead to improved outcomes. And what the goal here is looking for algorithms that could take the context and say what should be done. And precision health is simply the union of these things, because in a system setting, all of these things interact. And we would want to sort of think about these. We can't do everything at once, but this overall goal of developing algorithms that provide actions that can optimize outcomes is the goal here. Do this in a data-driven way based on reproducibility properties. And so I'm going to go now into a little bit of math and getting a few of the ideas. We're going to first talk about a very simple decision setting for precision medicine or precision health, where we have where we want to make one decision and we want to come up with an algorithm for that type of decision. So first we have our other tailoring variables. These can be thought of as context. You could think of them as biomarkers, phenotypes for individuals. It could be they don't have to be necessarily fancy genomic phenotypes, although they could be, but they could also be demographic information, other things that might affect how a patient what treatment should be given to a patient. And then, of course, the choice of treatments or potentially modifiable risk factors we want to look at adjusting or considering, and then a vector of outcomes or utilities. These are the things we want to measure to make sure that they are, or the outcomes we care about, to make sure that we can optimize those for a patient. And so this multiple, so anyway, these three variables are key ingredients, and we would collect a range of those for a range of individuals. In some cases, we can do it over time as well and get multiple copies of this or similar types of variables for patients over time. The dynamic treatment regime is an algorithm that we estimate use of this type. In the single decision setting, we would collect data that would allow us to make a really good idea of how to treat a patient for particular set of X, which choice of A should be given to them to optimize the Y that we're interested in. In the multi-decision setting, we're looking at a series of interpretations over time that can respond to how well the patient does as treatment is given to them and as they're followed. This can be done over where one gives a treatment and then checks in several months later, or it can be continually monitoring, as in the type 1 diabetes example, and using, for example, mHealth as an approach to data collection and recommendation generating. One of the key ingredients to this kind of research is heterogeneity. In precision health, heterogeneity is our friend, not our enemy. Homogeneity can be the enemy. We want, and I use the word context to collectively refer to the phenotypes and the other information we have for a patient, as well as their environment that they live in. That could also be a factor. And so we want heterogeneity of patients so that what we come up with will represent the broad population under a broad range of conditions. We also need heterogeneity of treatment assignment that's observed in our data so that we can determine best treatment under a variety of situations. The idea is you're not going to learn anything if you don't have a range of people experiencing a range of treatments. I think that intuitively makes sense, but it's just an interesting way that can be different than some of the things we do when we're looking at more traditional clinical trials, where we really want to try to reduce heterogeneity to decrease variance. Okay, here heterogeneity is our friend, especially if it's heterogeneity that we can measure with through this context, through this feature variable X. So a dynamic treatment regime must be an algorithm that we plug in the value of X. It could be entered in the computer, it could be just looked up on a table, and that algorithm tells us which of the treatments to give to that patient. And let's think about the data for estimating such a rule. We could imagine a randomized clinical trial. I know I said that we want to go beyond the homogeneity issue, but randomization is still good. Randomization will always help. But suppose we have a heterogeneous group of patients we randomize treatment to, and we have data from this, and we want to use it to estimate an algorithm for treating those patients. And so what we would do is we first could just estimate a regression equation that predicts Y, which we measure, And for now, we'll simplify, and Y is just a single outcome, such as total weight lost over the time period of the study, say, and then X is the baseline features of the patient, X, and A is the treatment that they were randomized to, the diet they were randomized to, for example. Treatment can be a range of possible ways that we would act. And we get this regression model. Now, it's important in this regression that we include the interaction between A and X in there. Otherwise, we're only going to be able to see whether A is overall beneficial or harmful. It could be that it's beneficial for some patients, harmful for others, in which case might mislead us into thinking there isn't much going on, when in fact there might be quite a bit going on for two different subgroups. And so we could directly estimate this decision rule from this Q of X. So now we have a regression model, call it Q hat, where hat represents its estimated from the data. Now, my algorithm becomes a patient presents with context X or features X. And what I would do is I plug it into Q, and then I try the different values of A, and whichever one gives me the highest one for that X, that's the treatment I give to that patient. And that becomes my algorithm for treating that patient. Now, let's look at this a little bit closer. There is a difference between prescriptive decision support and prediction. One might say, well, if I have a good Q, aren't I just predicting? Well, yes and no. So let's be very specific about our Q. Remember, I mentioned the importance of interaction. Let's let our model be the Y is equal to some f of X plus A, where A equals 1 if we have this treatment we're examining, and let's say that 0 is standard of care. And then we have G of X, which is the effect of the treatment as a function of the features. So that seems like a very reasonable and general model, right? Well, in decision support, to decide which treatment to give, we only need to know G of X. In fact, all we need to know is whether GX is positive or negative. If GX is positive, I know that giving that treatment will benefit. If it's negative for those people for which GX is negative, I know that giving that treatment and not the standard of care is going to be harmful. And so what we know here is that there is something important about the f of X component here. It tells us how well a patient will do. We call that prognostic, because it tells us how well a patient will do, but it doesn't tell us how well about the treatment and how the treatment will affect that patient. And that's the G of X. And so we call that the prescriptive part, because information GX tells us how to construct an algorithm to treat that patient. In this case, the algorithm is simply an indicator that G of X is greater than 0. If its indicator is 1, we give the treatment the novel treatment we're looking at. If it's 0, we give them the standard of care. Now, that's in a randomized trial. More generally, we may have a distribution of treatments across patients, and there may be various reasons that patients are getting different treatments. One of the things we'll want to look at is something called the propensity score. And this is the probability that a person gets treatment A given X. And we can estimate that from the data. In a randomized trial, we know exactly what it is because probability to get a treatment in that randomization, if we have an equal randomization, it's just going to be completely independent of X, and we'll know the randomization probabilities. But in other data, we would have to estimate that. And to be able to do precision medicine with that estimated data, we would need to make sure it's positive for all X. Now, there are alternative approaches that involve matching, and that works also. But in some cases, matching, you have to reduce the heterogeneity of patients you're looking at. Now, if we were doing this with propensity score approach and we didn't have positivity in that there are patients who are not getting treatment, we may have to also reduce the number of X's that we can look at, and even the population we look at a little bit to get some answer about precision health. Okay, that's a little more detail we need to get into right now. But the point is, propensity score contains valuable information about what kind of questions we're going to be able to answer and what kind of algorithms we can estimate from this data. Now, causal methods allow us to do this in a way that's give us results that are likely to reproduce. They give us insight into what assumptions we need to make and what we're trying to accomplish. So that what we get when we estimate these algorithms is causally valid. Potential outcome is just asking ourselves, what could this patient have gotten had they gotten treatment 0 or treatment 1. In a study, we would usually only, if not always, only observe one of these. In a crossover study, we might be able to observe both, but there might be some contamination in our estimate due to the washout not being long enough or something. But in a typical randomized study with just a single randomization per patient, we would only observe one of 0 or 1. And the idea of no unmeasured confounders is that if I can condition on those other confounders I have access to, every one that I have, and I get independence statistically of Y0 and Y1, then I can proceed with a causally valid analysis. If not, I have to do other things to be very careful, and sometimes I can't do it at all. So the idea of no unmeasured confounders means that X is all I need. There's not any missing variables for which to affect treatment that we don't observe. And I recently worked on a study where we drew confounders that were dictating treatment. And so we had to think about, go on to other methods. All right. I mentioned the positivity assumption. Okay, so this is some ideas about the pipeline. Just then give a causal framework for what we're doing. Let's go back to the DTR estimation idea. And you will hear when people talk about precision medicine, they often talk about precision health. They often talk about algorithms. Oops, sorry, I went too far back. The main idea for the algorithm that we're discussing here is a dynamic treatment regime. That is the algorithm that typically you would want to use in this setting. Oops, I already talked about back here. In the single decision setting, which is the example I just kind of went into detail with the Q regression function, regression and then maximization of that regression model, as I described, requires fairly standard statistical tools and machine learning tools. Just regression prediction, as long as the interactions included are sometimes sufficient if the models are correct. And both frequentist and Bayesian tools can be used here. And if we have really complex regression modeling, machine learning can be very helpful. We could even use deep learning if we wanted here. In the multi-decision setting, we start having to use some new statistical estimation tasks that are not typically the standard things we often learn about in our introductory statistics courses, and even in some advanced statistics courses. What we need in the multi-decision setting is something called off-policy reinforcement learning. Really, reinforcement learning is a machine learning tool to learn after a sequence of actions how one should respond to a given context or situation in real time to get an optimal result. A lot of the early work was used for robotics or in games, developing computer game tools, or playing games, for example, by AI. But we also need something called off-policy, which is quite different than a lot of non-human health-based reinforcement learning, because when we work with patients, we often cannot give them multiple treatments to try, and we basically can give them one treatment at a time, and we can't. In some cases, we can only give them a small 1 or 2 treatments depending on the setting. So Q learning is especially useful in this situation. That's an example of reinforcement learning. There's some very nice off-policy approaches. This involves a sequence of standard regressions that we do some other things involving maximization and adjusting the outcome we're estimating and doing other things. And random forests and deep nets and other tools can be used here, but it's distinct from regression in the sense that you can't have regression steps, but the overall estimate. So a couple of recent developments in this area that were specifically developed with human health in mind and random trials and observational data. Outcome-weighted learning is the focus here is on estimating that algorithm itself directly without having to estimate the other components of the regression model. Sometimes benefit from that, including lower bias and other benefits. And the outcome-weighted learning does this by converting the dynamic treatment regime estimation problem carefully to a weighted classification problem for which there's decades of machine learning and statistical tools available to solve. And we can get that algorithm directly. And there's a number of benefits to the outcome-weighted learning idea. It's kind of interesting because really the basic idea is let's take a randomized trial where you have equal randomization in two treatments. What you do is you pretend like you're classifying and predicting treatment based on the feature variables X, which is not particularly wise since those are randomized. However, if we weight each one of the classification errors proportionally to the outcome Y, assuming bigger values are better, actually, and then we solve that classification problem using a surrogate such as would be done in support vector machines and other machine learning styles, you actually get the classifier from that actually is the algorithm that will optimize the expected outcome for patients. So it's an interesting where we take one problem that is the incorrect problem, but by reweighting, we get the correct problem. So there's a number of extensions to that. Now, so this is at a high level. There are the point I want to make, and we'll come to some specific examples, is there is over a decade of work that's been done at laying a very rigorous, causally valid foundation for estimating these algorithms. And there's a number of tools that allow us to do this efficiently and effective and allow us to leverage a lot of the power in modern machine learning tools. And just a reminder, machine learning and AI, they're largely alternative ways to estimate and predict things. And so essentially they are statistical analysis tools as well as computer science tools. But these are tools that allow us to take data to learn things and to do various things. And so one of the things that can be a little bit confusing to people is what's the difference between statistical analysis and machine learning? Well, historically, the difference was maybe that there were some computer scientists that were developing in one certain category of ideas, and there are statisticians developing others. More recently, there's so much overlap that there's statisticians and computer scientists both contributing to this very rapidly. It's an area where both computational, subject matter area, statistical expertise, all three are needed to do well in this area. I want to take a little tiny detour into the idea of artificial intelligence, because that's the big group of methods that include machine learning and other tools that encompasses many of the techniques and tools that we'll be looking at. And I say that all of them, to some extent, are applicable to this type of algorithm estimation, depending on the goals, depending on what you're doing, the kind of data you have. And so AI is very relevant to this. And I just want to go over a few little things I think are kind of interesting. I'll try to I'll bring a connection back to what we're talking about. But in the early days of artificial intelligence, 1950-ish, the idea was to develop something that looked and mimicked like a human. And the Turing test is, can it do it so well that we can't tell it's not a human? And so that was the idea of a Turing test, to test AI to see if we could tell whether or not it was a human. And that's one way to think of this. Another way that is slightly more practical is, what can we have it learn to perform tasks that people perform and maybe do them better than humans do? For example, a human would make spelling errors. And so we could quickly tell, if we asked a really hard word enough times, we might be able to suspect that an AI knows more than a human in terms of spelling, and it wouldn't look like a human. So that's not necessary, but we do want to have help with spelling. So there's a distinction between these goals here, making it look like a human or having it perform tasks. How about reason logically? Could we have it reason logically, like maybe better than a person? Could we have it be able to make an optimal decision in a situation or that will lead to good outcomes? And that's really what we're talking about with decision support in the health area. How can we actually have an AI act optimally? Now learn how to prioritize. I mentioned the vector of Y's, the outcomes. What is to optimize in health? Is it always survival time, or do we need to look at quality adjusted survival? These begin to be harder and harder questions. How about reasoning morally? Can we teach it to reason morally in a random context? And then how about, can we have AI learn to create something that's fantastic and surprising? Right now, it can recreate art that's similar to other things, Mozart pieces, little snippets of it that sound like Mozart, but can it create a new piece that would make musicians, composers, and say, wow, I've never heard anything quite like that, but it's really nice. Not yet. They cannot do that sort of thing yet. But what do we really want computers to do? Probably just help us in various tasks would be one way. Help us make better rational decisions to achieve predefined goals. And goals are usually related to optimizing a predefined utility. And so computers could certainly help us do that and help us do more. And these are some of the goals that are being worked on with computing, and there are many, many others. I'm just listing those that I think are directly relevant to precision health. And so one way to think about this, if we just step back from all of the things that AI can do and just focus on the things that we're really potentially interested in, they're related to prediction. And the first stage of prediction is to just try to predict the outcome based on the variables we have available for predictors. But then we'd like to be able to have that prediction be causally valid, so that if I change some of the changeable parameters like treatment, or maybe potentially modifiable risk factors like smoking or diet, can I predict what will happen to those patients? That's sort of being able to have the prediction go to what if analysis capabilities. And then the further on would be the decision support. Not only what are the things that might happen if I tweak things, but I'd really like to know the optimal combination of treatments that I need to give to these patients in these different contexts. This is the algorithm part here. And that's the thing that we're discussing here. And this just tries to give an idea, because oftentimes in AI world, we're solely focused on prediction, but really there's so many possibilities, and the things we want to do in precision health go so far beyond prediction, and they're things that AI can help us with. This is something that people always talk about with AI is AI winter, but I think it's actually kind of relevant for anything that involves research where there's a potential interest that may wane after hype is not achieved. And this certainly has happened, and people have cataloged what's happened over the various winters of AIs, where there's great promise and it kind of petered out and people lost interest. And then a new thing came up and is a great promise. We are currently in sort of a hype cycle because there's so many things that we're learning how to do. And the winters are not necessarily totally devoid of progress. Oftentimes what happens is the hype is gone, but people recognize real promise, and the day-to-day careful research is being done to sort of keep improving these things so they're very useful. Some of the most useful AI tools that we use today came about during winters where traditional methods there were no new fancy AI tools, but traditional methods were refined and improved until important breakthroughs were made. Now, I want to switch to another high-level discussion. That's just to give you going back here, what does this mean for us? Well, with precision health, everybody's really, really excited about it. And let's do precision health. But when it gets down to it, the real hard work is these algorithms. Other things can be done. We can collect huge amounts of data. We could do prediction. But is a prediction good enough to actually improve how we treat people? And that, or what actions are taken, what policies are made to improve health? That's the hard work. And that's what we need to take time to, one of the things we need to do. So precision medicine, if no great discoveries are, so we don't focus so much on the hype, but focus on the work we need to do to have realization of the goals of precision health. Okay, now the dark side of AI ML. There's several dark sides, and these all have silver linings. But with every, there's a few things I want to mention that are important. One is the democratization of AI. Right now, TensorFlow is easily accessible. There's packages in Python. If you learn those languages, you can have a deep learning net and start work with it and try to predict some things from data that's collected online. It's easily accessible. Okay, that's actually not bad. We want people to be, citizen scientists, and we want them to be informed. But what happens is, and so it's definitely good because there can be greater awareness of AI. There's greater citizen science progress. But what's the con for this? Well, we've already seen this happen. But if there's insufficient understanding of statistical principles, including reproducibility, there are either too many false positives or there's biased data that the results are biased and we take them too seriously, and they can really take years to fix and cause a lot of problems. I can list a couple specifically, but one of them is we could waste time before we realize that it was wrong. And there's some there's some analyses and results over the years. I don't want to go into actual examples here, but that can be a problem. It's already been realized. People have to be very careful with how serious they take the results. And if those methods used are grounded in good statistical principles, they can lead to significantly powerful results. But if we're not that, we could be misled for a time and waste time with false algorithms that aren't really working. Another worry is the risk of bad actors. We have people who can figure out how to do it right, but they use the AI to harm people. And this could be done intentionally or unintentionally. Examples are early versions of some of the search algorithms and machine learning were able to increase clicks by encouraging, although it wasn't intentional, I don't think, increased discord and conspiracy theories. However, I think that's been addressed over the last few years. It's beginning to address, at least in part, but it needs to be addressed more carefully. That was largely unintended, but one can imagine if there are intended bad consequences, that could be very dangerous. The other thing I want to mention is that good research takes care. Sometimes we think that something that's done quickly and is impressively flashy will be the right solution. Sometimes the right answer just takes hard work. And I will say that that's very true with precision health. It takes more time than one would like it to take to come up with these algorithms in ways that seem to be likely to be useful in practice and to validate them. But I think it's ultimately worth it because a lot of worthwhile things are hard. But another issue is that if there's too much impatience, this can lead to poor evaluation and peer review, which could lead to problems. And then we could get a lot of things published and out there that are performing poorly, and then that can reflect poorly on the whole field, and funding can be reduced when in fact there's a lot of good stuff too. So it is important that we're careful with our research. Now, the other thing is study design is very crucial in all of this. The better data, the better the machine learning, and if the data is bad enough, no amount of powerful machine learning will fix the problems. This score here, the thing in the middle here is a score it's a photocopy of original score by Beethoven of the Fifth Symphony, which those of you with musical background or not, well, many of you have heard that symphony, but from one of my serious hobbies is composing, and many people consider the Fifth Symphony to be significantly by far the best symphony ever written, and it took him a lot of time to write it compared to other symphonies that he wrote and others wrote. He was trying to do something so new and such a surprise that he really had to take his time, and he wanted the execution to be flawless, and it turned out to achieve all of that quite successfully. But it took time. That's just a point there. It also, every opportunity I have to talk about music, I put it in my talks if possible. Okay, so let's go back to these examples. So what kind of thing can be done? Method could be used to develop an algorithm that could allow and give suggestions for a patient on how to exercise, how to eat, how to do other things, how to receive insulin, so that they can safely exercise. and be able to keep their glucose level within control. So this is the goal of a project we're working on using reinforcement learning. We're using a number of tools for this, but the most important thing is we're using off-policy reinforcement learning, and we're trying to restrict the amount of modeling we do. So the framework we use in the Markov decision process. Now, of course, the fact that it's Markovian, that's already a little bit of modeling, but there's a lot of things we're trying not to model too much. And one of them is the transition probabilities. We try to model directly the algorithm, or as close to directly as possible. We can think of this as sort of an extension to the multi-time step, real-time decision-making of outcome-weighted learning. And I'm just giving a little bit here, but the method so far works quite well. We were able to apply it to some data and get a 64% improvement of time a patient could stay within range by using the recommendations of this approach, keeping their glucose within a safe range. And it's still in the process, and the works are being developed and being to prepare a prototype is being developed, and the goal is to eventually have this used by patients. So that's in the works. Another example that some of you that are in this meeting today were involved in was an algorithm for precision treatment or precision decision making for treating patients with knee osteoarthritis. And the idea, this data from the IDEA trial was reanalyzed. We had a range of variables at baseline. We had 343 participants, and there were three treatments: exercise only, dietary approach only, and then a combination of the two. So those were the three that were examined, and we were able to estimate an algorithm that turned out to be statistically significant in its improvement. I will say that when one does discovery algorithms like this, well, the chance is high for reproducibility because of the nature of the algorithm. One still should do external validation of these things. That's the ideal. And the algorithm here that was determined is that some patients would receive diet only, and some would receive diet plus exercise. It was in this, exercise only didn't seem to benefit anybody. And our algorithm is a function of the weight at baseline, waist circumference, and whether they have a history of heart disease, but it ended up being a fairly simple algorithm that we came up with. Okay, so that's, I wanted to I'm just giving very high level ideas of this. Another thing another example that I want to present is a completely different goal. So the previous two examples were examples of algorithms that we estimated. One was for real time, one was just for a single decision, what treatment to give a patient when they present. And I am oversimplifying the clinical context just a little bit, for which I apologize, but I'm trying to just give a somewhat simplistic view to sort of make to add clarity to the methodology. But one of the, comes from some research with bipolar disorder, and this comes from a study called the STEP-BDE SCP study. It was published in England Journal of Medicine, I think in 2015. There was an observational piece and a randomization piece. Well, we're going to actually look at the observational piece now. One of the challenges I mentioned earlier is that you could have more than one outcome. When you have a single outcome, like the two previous examples, well, the second example actually has multiple outcomes, but I skipped over that. But the first example has just a single outcome of keeping glucose within range. And at least that's the current version that I presented. But sometimes we need to weigh multiple outcomes and use that to help with our algorithm and figure out. And so one of the goals we had here was, let's say, presume that physicians who have expertise in bipolar disorder really know how to treat these patients, but they can't do it perfectly. They make it with some mistake. And let's model the probability of them doing it correctly with a logistic model to be simplified here. And let's say that and we're using observational data. So we see what patients they treat, and we also measure the outcome. And let's say that our goal is to figure out how physicians are prioritizing the two outcomes of depression versus controlling depression versus controlling the mania. And then use that to guide us to come up with specific outcomes for the individual that we then would give them the specific treatment that maximizes that outcome. So this allows us to replicate what clinicians are trying to do, but to get past the error and get underneath to the algorithm that is actually being used. And so we developed a method of inverse reinforcement learning. What this is you look at these contexts where you're treating patients and looking at the outcome. Are they being treated? In this case, you can only use observation for this because we want to look at how physicians are prioritizing. In a randomized study, they don't have control over the treatment, so you wouldn't learn anything about that. So here, we actually need observational data. We still have to control for the confounders and so on, as you would do for any other setting, but it's a different way of looking at precision medicine, asking a question that's still important, but perhaps a little more complex, and that is, how do we decide between outcomes, which is best? One can also use patient-based information to do this. That's a subject for another talk. But we found that we were able to do this, and we were able to improve the outcomes with this data set based on our estimated algorithm by a significant amount, in this case, 7% improvement in overall performance. P-value is 0.001. And we also looked at trade-off between controlling depression and side effect burden, and we're able to improve that particular trade-off by 9%. Currently, the method only can handle looking at 2 different outcomes. We are also working on handling more than 2 and trading those different utilities out to come up with sort of the patient-specific utility that the clinicians are using in this context. Okay, so there are some complicated things there. And I just wanted to give you an idea of some of the things that we can do and some of the questions we're trying to ask. Our goal is to improve decision-making in human health. And as you can see, there are a number of aspects to that. There is the outcome we want to optimize, or the collection of outcomes we have to prioritize. There are the actions we actually want to take, treatments or doses or whatever. And then there's a context that may change over time that we want to use as the input to our algorithms. And so you can see that these are non-trivial things, but our goal here is to come up with approaches that are reproducible, will work in new patients, have statistical validity, and will actually work with new patients in new contexts in the real world. Now, this very complex diagram, I only want you to see and say, wow, that's complicated. But the idea here is a vision that we have for the future, and there's a paper that we wrote on this that gives a little more detail, is that we envision a world where experts are interacting with data and collecting in such a way that we can make decisions in real time, because our goal is to do this algorithmic development, that we can adjust the way we do this so that we have the right utilities, that it can change over time as patients change, and that we can keep learning and improving in the way that we're doing this. And so this is sort of a vision for continually adapting or real-time decision-making that is being done, and that it's being monitored so that there aren't any unintended consequences. For example, one can come up with an algorithm that seems to be improving health, but it may be harming an underrepresented group. All of these things need to be taken into consideration. Okay, so as I wrap up here, I just want to, at a high level, how does one go to prepare for the future here? Well, the first thing I would say is we all need to commit ourselves to do good AI ML science, which means we need to make sure that we're thinking about the statistical issues and the computational issues both. But statistical is more focused on the reproducibility question, which is extremely important as we want to create algorithms that will actually work on new patients. And rigorous team science is really needed to achieve the depth for this. So this is the kind of thing we need to do. We need to think about the ethical implications of what we're doing with AI and machine learning, and examine the various things and develop strategies to keep our society safe and to keep the ethics in a good place. We need to train the next generation in new ways With increased democratization, we need to find ways to democratize statistical principles a little more too, and make sure that people know those along the way. We need domain area expertise when we're working in this decision support, because this cannot be done with an absence of the system context. And so all the tools that we've been talking about were developed in collaboration with clinicians, in fact, and clinical scientists and other domain experts. In fact, even many of our statistical papers have clinicians on them because we're trying to develop our methods so they are applicable in these situations that we become aware of as we collaborate with individuals and we learn about it from other research groups. And then we need to learn how to communicate better about these various things. Doing this sort of decision support, as you can see, it's fairly complex, but nothing we're doing is counterintuitive or once you see what's going on, I don't think there's any real big surprises here. There's sort of the kind of building blocks that one would need to be able to rigorously evaluate these approaches. But nevertheless, it takes work to learn these areas. And we want to find ways to communicate about AI generally and about precision health. And probably could benefit from disciplinary expertise in communication field where they focus on these sort of types of communication. Because there are various reasons, but the role of public opinion is important in the implementation of these things and in various other ways. And so this communication is very important. So a few concluding thoughts. Well, first off, there are many useful new methods in AI and machine learning for precision health discovery, especially in decision support, which is the focus that I'm describing. And that's what I usually think of when I'm thinking of precision health. We need to go beyond prediction as a focus in machine learning and in a lot of other research contexts and think about decision support so we can do these more difficult tasks and learn how to do them better. Statistical inference principles are key to reproducibility and generalizability, and essentially they're key to making sure our methods work in practice and not just to testing them afterwards. If we do terrible work at building them in the first place, without statistical principles, their reproducibility, power for precision medicine. Our goal is different than other things, but our goal is to get within 90% of the true underlying algorithm that will benefit patients the most with at least 80% or 90% probability. And so that's a very, it's hard to do, but that's what we're trying to do. And so our method bias is designed to have inherently built into it reproducibility properties. And that's very important because a 90% probability of being right is different than a random chance with a 1 out of a million chance it'll be good. And so I'm just pointing out here that it's not just evaluating that you need statistics, you actually really need it at the very early data collection and machine learning stages. So, and this, we need to embrace transdisciplinarity. This field is moving very fast. We need experts in so many areas. Optimization is another area that is very important to this. A lot of work remains, and we have not come this far just to have come this far. Okay, that's the end of my presentation. I guess I'm going to go to questions.
Thank you, Dr. Oh, go ahead.
I could stop share, just leave it here if there are questions related to the slides.
Okay. Well, thank you, Dr. Kosorok. Just to remind everybody, you can either unmute yourself and ask the question, or you can type it into the chat box and then I will read it aloud.
Hi, Dr. Kosorok. Thank you so much for your presentation today. I guess I just have like a question about kind of like just in practice. But let's say, for example, you're trying to like help a doctor make a decision. How do you go about into like quantifying like a person's death, or like the cost of like your function if something goes wrong, or like what are like steps that I guess you would want to like consider for you to be able to like appropriately kind of like weight in the model, like the health of a person, just because I feel like in this context, we're not just like making a decision over like whether to buy a stock or not, but we're actually making decisions about a person's kind of like health or whether they live or not. And I guess like how do you account for that in a model?
So
Thanks.
let me see if you're asking for how you account, what account for, I'm trying to figure out what you're accounting for. The fact that there could be a mistake in the algorithm, is that what you're saying?
Yeah, and I guess also how that relates to like
You're talking about cost of mistakes, right?
yeah, yeah.
For example, so one way to handle that, if you can factor cost into the utility that you're maximizing, you can also do things where you minimize the worst case of your outcome, like the top 5 percentile. And oftentimes, I think that a very good way is to interact with patient representatives, for example, and clinicians, to see if you can make sure that you're looking at the right priorities for them in the first place. Right now, in this situation, we looked at what clinicians were trying to do with the understanding that they have a feeling about the big picture. And so they're going to pick good short-term utilities that will maximize an overall long-term health benefit for these patients. At least that's what we're thinking going into it. The thing is that all decision-making is subject to error, right? And so sometimes even with experts don't know exactly what's best, but they have they get close a lot. I will say that we have worked on studies where the clinicians seem to really have a good understanding, because when we went back to reanalyze the data and try to improve on the algorithms that the clinicians were using, we could not get better outcomes than they had. And other studies where we could see a pretty big improvement. And other studies where there's randomization involved because the clinicians don't really know what's best. And usually, sometimes it's a mix of both of these things. So the kind of the kind of setting really depends on how you trade these things off. And cost, I think, is definitely one of the things you can factor into the utility, including cost of mistakes. It's a great question. Thank you. What?
And then I guess I just have like another follow-up question. But I guess when it comes to like developing kind of like these machine learning models and artificial intelligence, and for them to have kind of like a positive outcome in society, but equally as a negative outcome if it's used for like the wrong purposes, whose decision is it to like maybe not release the research? Would it be the scientists, or would you say it's the government, or who is the governing structure that should oversee whether research is appropriate for like public use?
That's a good question. I would say there's a huge, we could spend hours talking about that, but I would say that many times scientists, I think if they know it's going to harm, or at least scientists that I've been interacting with, would not want to have it released. So they don't intentionally want their work to harm. Other times, there's nobody watching over an algorithm. It may be developed by a company for a purpose that's not bad on the face of it, but it may have unintended consequences. And so there probably is a need to ask the question, who should be responsible for these things? I do think scientists should be responsible for everything they know as much as possible, but even the scientists can't predict everything that's going to happen to their tools, but certainly they can prevent things that they know will be harmful from going out in the public. But I think that's a good question. It's a challenging one about oversight, because you want some oversight, but not too much, right? That's the difficult thing. And I think that's really hard question. It's a great question. So thank you. I noticed that somebody asked a question, what is meant by off policy? Well, what I would say there, just want to give a little bit of an idea. On policy is where you take the context and the situation and you try a variety of policies and algorithms out, which you can do with a game or a robotics where you can simulate something. However, if you have a patient and you have a randomization in a trial, you can only randomize them typically to one treatment. You can't repeat the whole experiment with that same patient because their health has changed, especially if it's a life-threatening illness. You can't just try different treatments without a washout period. So what we do is we take the data as is, where many of the patients are not experiencing the optimal policy or the optimal treatment because we didn't know what it was in advance. And we use that off-policy data to estimate the true policy that will optimize patient outcome. So patients are precious in human research. We can't give them this, we have to be careful how many times we treat them. We have to be we are very restricted in how we experiment with patients for very good reasons. And so that's one of the reasons we do off policy for the most part in biomedical research, but it's not a restriction in robotics and in gaming and other areas.
Thank you. I just have another question, I guess, which is kind of a good follow-up to that question. So if heterogeneity is your friend, then would you require larger sample sizes for your trials as compared to a less heterogeneous population?
It depends on the goals and other things, but sometimes what's interesting, if you sample size, let's say we're doing a single decision setting where we could just use a randomized trial. Well, sometimes if you size the trial for just looking at the treatment effect, it's often pretty well powered for coming up with the algorithm afterwards. Sometimes not. And so the other thing one could do is do sample sizing for the just treatment comparisons, traditional approach, and then sample size for the algorithm and take the larger of the two. Other settings where we have more complex study designs designed to look at sequences of treatment, such as sequential multiple assignment randomized trials, we look at the many possible treatment paths that are there, and we would need to be careful. However, if you have continuous treatments in other contexts, the sample size that you need to get an algorithm is way lower than one would expect if one were trying to power for all of the beta components that went into the model for that algorithm. If one wants the power to get all of those precise, you may need millions of times the sample size that you actually need to just get an algorithm that is very, very close to optimal without having the parameters being within a certain, without having the statistical, without having to have high precision on your parameter estimates. Especially in models that involve a large number of parameters, this will be true, like random forests or deep learning. So not as large as you would expect, but sometimes larger than traditional randomized trial settings.
So we're about at time, so if anybody has any last minute questions, feel free to ask them. Okay, well, thank you again, Dr. Kosorok, for talking to all of us today. Just so everybody knows, I'm going to be sending a follow-up email to everyone who attended in the coming days, just to let you know kind of how to access this recording. And then also you can just share with other people if you want to share with your colleagues or put it on your website, things like that. Prior to everyone leaving, it'd be great if you could complete a brief anonymous survey about the presentation. It kind of helps us figure out how to move forward with future presentations. And again, thank you, Dr. Kosorok, for the wonderful presentation and everyone for attending. I hope everyone has a great day and weekend. Bye.
Bye, everybody.